Our understanding of the universe's origin and destiny has transformed. This revelation didn't just reshape cosmology. It forced us to confront our place in the vastness of space, revealing that everything we are is built from elements forged in the fiery cores of long-dead stars. By 1957, scientists had come to widely accept that the night sky is far more than a beautiful tapestry of pinpricks of light. It is a window into the astonishing physical processes that drive the universe itself. This universe is anything but static. It is alive with motion, mystery, and profound transformative power, much of which remains beyond human comprehension, prompting us to ask age-old questions about why we exist, how stars and planets came to be, and whether life might flourish somewhere else among the stars. Yet for all our curiosity, it is human nature to overlook the grand drama of cosmic evolution until something spectacular or threatening catches our attention. One such focus of fascination is the giant red star Betelgeuse, a massive supergiant located in the constellation Orion. Unlike the ordinary stars that sprinkle our skies, Betelgeuse is one of the largest and most luminous visible to the naked eye, with a radius over 1,000 times greater than our Sun. Despite lying more than 640 light-years away, a distance so great that even light traveling at 300,000 kilometers per second takes more than 6 centuries to cross, it blazes brightly in our winter nights because of its sheer size and intrinsic luminosity. This incredible scale hints at the raw power contained within such a star, a power that has drawn scientists' attention for its visible instability and potentially catastrophic destiny. Betelgeuse is a variable star, its brightness changing over predictable cycles driven by the slow expansion and contraction of its vast outer layers. These pulsations, one cycle of about 185 days and another closer to 2,300 days, act like a cosmic heartbeat that betrays the star's turbulent interior. When the star expands, its surface cools and dims. When it contracts, it heats up and brightens. This rhythmic breathing reflects deep internal processes that are anything but gentle: vast convective currents, roaring fusion reactions, and shifting balances of gravity and pressure. In recent years, however, scientists have observed worrying signs of increased irregularity in Betelgeuse's fluctuations. In early 2021, its V-band brightness plummeted to one of the lowest levels in decades, a deviation that suggested profound changes were underway inside. This star's distinctive reddish glow comes from its relatively low surface temperature of about 3,500 Kelvin, far cooler than our Sun's 5,500 Kelvin. That cooler temperature, combined with its immense size, creates its iconic hue but also indicates an advanced stage of stellar evolution. For red supergiants like Betelgeuse, this phase marks the late chapters of a star's life. Having exhausted the hydrogen in its core, Betelgeuse has shifted to fusing helium into heavier elements like carbon and oxygen, a process that is far more erratic than the stable hydrogen fusion of its youth, known as helium shell burning. This new mode of fusion is turbulent and uneven, releasing bursts of energy that destabilize the star's structure and drive fierce stellar winds. These winds expel enormous quantities of mass from its outer layers, further upsetting the balance between pressure and gravity that keeps the star from collapsing. From Earth, these changes are detected through the careful science of photometry and spectroscopy. Photometry tracks changes in the star's brightness over time, while spectroscopy splits its light into a rainbow of wavelengths to reveal temperature, chemical composition, and motion. Together, these tools allow scientists to build a picture of the star's life in exquisite detail. Advanced computer models combine these observations with the laws of fluid dynamics, thermodynamics, and nuclear physics to simulate the star's interior, predicting its future evolution with increasing precision. A crucial factor in these models is the role of convection, massive currents of hot plasma rising and falling through the star's interior in a turbulent cycle that brings energy to the surface. These convective cells can create giant upwellings of material, forming cool patches that dim the star or hot spots that make it blaze. This dynamic activity came dramatically into focus during Betelgeuse's great dimming event of late 2019 and early 2020, when its brightness dropped to unprecedented lows, sparking speculation that it might be on the verge of exploding. But careful observations, including data from the Hubble Space Telescope, revealed a more nuanced explanation. A giant convective plume had risen to the surface, ejecting an enormous cloud of plasma that cooled and condensed into dust, partially blocking Betelgeuse's light from our vantage point. This revelation highlighted not just the star's instability, but the raw power of its internal processes that are critical for understanding how massive stars live and die. Ultimately, Betelgeuse is on a trajectory that ends in spectacular destruction. When it can no longer maintain the balance between internal pressure and gravity, its core will collapse in a fraction of a second, triggering a supernova explosion of unimaginable scale. For a brief time, Betelgeuse will shine as brightly as an entire galaxy, outshining the moon in Earth's sky, even visible in daytime, before fading to leave behind a dense neutron star or possibly a black hole. Though most estimates suggest this event is likely thousands or tens of thousands of years away, the signs we see now, the irregular pulsations, the mass ejections, are the foreshadowing of that cataclysmic finale. Yet this violent end is not only a death but a rebirth on a cosmic scale. The explosion will scatter heavy elements like iron, oxygen, silicon, and carbon, elements forged in the star's core, into the interstellar medium. These will mix with vast clouds of hydrogen gas, seeding the next generation of stars and planets. This is how galaxies evolve, through cycles of stellar birth, life, death, and rebirth, each generation enriching the cosmos with the elements necessary for life itself. In this way, Betelgeuse serves as both a window into stellar evolution and a reminder of our own origins. For every atom of carbon in our bodies, every molecule of water, was born in ancient stars that exploded long before Earth existed. As astronomers continue to study Betelgeuse, they're not just watching a single star, they're gathering data that transforms our understanding of the universe. Instruments like the James Webb Space Telescope and Hubble allow us to peer through the dust clouds that obscure the star in visible light, revealing its structure in infrared detail that was unimaginable a generation ago. Ground-based observatories use interferometry to combine multiple telescope images into one, resolving details on Betelgeuse's turbulent surface and tracking convective cells the size of our entire solar system. Techniques like astroseismology, analyzing the tiny oscillations in a star's brightness, offer clues to its inner density and composition, much like earthquakes reveal Earth's interior to geologists. Betelgeuse has thus become a natural laboratory for testing the physics of fusion, convection, and mass loss. It helps us forecast not only its own supernova, but the eventual fate of stars like our Sun, which, though far smaller, will one day expand into a red giant, shed its outer layers, and leave behind a dense white dwarf. The processes are the same in principle, even if the outcomes differ in scale. For Betelgeuse, that outcome will be dramatic, a supernova so bright it will alter our experience of the sky for months, casting eerie shadows at night and reminding humanity of the forces that shaped our galaxy. Such an event would also be a once-in-a-civilization spectacle. The last naked-eye supernova occurred in 1987 in the Large Magellanic Cloud, 170,000 light-years away. Betelgeuse, by contrast, is in our galactic neighborhood. Its explosion would not just fascinate astronomers, but unite humanity in wonder, offering a visceral, shared reminder of our place in the universe. For now, scientists wait, watch, and refine their predictions, knowing that every new measurement contributes to a fuller understanding of stellar evolution. It is a patient science, a global collaboration among observatories, satellites, and space agencies. More than any single star, Betelgeuse reminds us of the universe's capacity for both beauty and violence, for destruction that seeds creation. It embodies the idea that we are made of star stuff, that our lives are bound to the lives and deaths of distant suns. Through its flickering lights and colossal storms of plasma, it whispers the truth that everything is connected, that in studying this dying star, we learn not only about physics and fusion, but about our own origins and destiny. Even as Betelgeuse's final act remains somewhere in the future, it offers us, here and now, a profound lesson in humility and wonder. As our telescopes probe its secrets, we are reminded that the universe is not a static backdrop, but a living, evolving system of which we are an inseparable part. Every observation is a step toward understanding that truth more deeply. And every time we look up at the night sky, we're invited to participate in that grand, ongoing story. As technology advances, our ability to study Betelgeuse will only grow more precise. Future telescopes, both on Earth and in space, will watch its every flicker and pulse with greater clarity, capturing subtle changes that might elude today's instruments. Scientists will refine models that simulate its turbulent core and predict its fate with ever more accuracy, while new generations of astronomers will inherit the task of monitoring its slow, majestic decline. Beyond the science, though, Betelgeuse also serves as a powerful cultural touchstone. It inspires awe-in casual stargazers and fuels the imagination of artists, writers, and dreamers who look to the night sky seeking meaning. The star's story reminds us that even the most stable-seeming things can change, that creation and destruction are inseparable parts of the cosmic cycle. In Betelgeuse's eventual demise lies the promise of new beginnings, elements that will someday become part of new stars, planets, and perhaps life itself. Watching Betelgeuse is more than an astronomical exercise. It is a meditation on mortality, transformation, and the vast interconnectedness of all things. It shows us that while we are small in the scale of the universe, we are inextricably woven into its grand, ever-unfolding tapestry. As we move deeper into the 21st century, Betelgeuse continues to offer not just an astronomical mystery, but an evolving scientific opportunity. New instruments coming online, such as the Extremely Large Telescope, ELT, in Chile and NASA's upcoming Nancy Grace Roman Space Telescope, will add even more precision to our observations, allowing astronomers to dissect the star's layers, pulsations, and atmosphere with unprecedented clarity. These advancements will also enable researchers to monitor the surrounding interstellar environment, detecting any precursory emissions, neutrino bursts, or gravitational waves that might precede a supernova. The hope is that when Betelgeuse finally reaches its end, we will not just witness it, but record it in real